Hypothesis testing for correlation. Suppose the analyst wants to see if there's a relationship between the returns of stock X and the return of stock Y. To test the hypothesis, the analyst is going to draw a sample, and this includes 40 observations, so this would be 10 years worth of quarterly returns. And the analyst calculates that the correlation among these 40 observations is positive 0.6. So this would be the sample correlation. Now here is the issue. This sample may have errors or biases and therefore may not be fully representative of the underlying population. Let's go back and look at the data we have so far. This correlation you calculated, that only represents 10 years worth of quarterly data. So based on the sample period you picked, you're going to get a different value for correlation. The point is, we don't know what the true correlation is between stock X and stock Y. And the fact that you're using a sample in order to reach a conclusion raises the issue that the sample might have some errors built in. So therefore, while the sample exhibits a positive correlation, which is positive 0.6, the question is it possible that the population correlation is insignificant? So what I'm going to do is I'm going to use that little p to denote the sample correlation and the r to denote the population correlation. And they're two different variables. So the sample here, this was calculated using 40 observations. But again, the population theoretically represents all possible observations. And what we want to know is, after we factor in the margin of error that comes with using samples, is it possible for the true correlation between X and Y to be 0? Now, even though we're going to be conducting a hypothesis test, this is also referred to as a significance test, because what we're trying to do is we're trying to prove or disprove the hypothesis that the population correlation is equal to 0. So it's a hypothesis test, but because it's centered around 0, we also refer to it as a significance test. So here's how it's going to play out. So before we do any quantitative analysis, if we reach the conclusion that this is possible, then our conclusion would be that the correlation is insignificant because it's 0. On the other hand, if our sample or our hypothesis test disproves that, then the conclusion is that the population correlation is significant, because then it wouldn't be 0. So let's go ahead and conduct our significance test. So first we state the hypothesis. So the null hypothesis is that the population correlation is equal to 0. In other words, it's insignificant. And therefore the alternative would be the complement of that. So if you reject this, it would mean that the population correlation is not equal to 0. The second step is the level of significance. Now this will be given to us. So if they indicate that the level of significance is 5%, that would indicate that they want to give the null statement a 95% margin of error. Remember, ladies and gentlemen, the hypothesis test is based on a sample, and samples have errors. So what we want to do is we want to give this null statement a 95% margin of error. The next step, step 3, we have to identify the distribution for the sample correlation. And we use a t-test in this case. And then step 4, we do the hypothesis test itself. Now, I always liken a hypothesis test to a penalty kick. And the way penalty kick works is as follows. We set up these goalposts, right? And if the ball comes anywhere inside the goalposts, it's a score. On the other hand, if the ball comes anywhere outside of the goalpost, then of course it's not a score. And it's the same thing with hypothesis tests. So with a hypothesis test, what we do is we put the null in the middle, and then we set up these goalposts around. Why are you setting up a goalpost around the null? Remember the margin of error? We want to give the null statement a margin of error because this whole test is based on a sample. So if the sample falls anywhere within this range, then we would go with the null. But if the sample falls outside of that acceptance range, then we would reject the null. It's the same thing. So just like penalty kicks, we need to find where the goalpost is, and we need to find out where the ball came in. And in the context of hypothesis test, the goalposts are referred to as critical values, and you see that over here. And the ball, in our penalty kick analogy, will be the sample statistic. And you can see how this framework here is very similar to penalty kicks. You could see here's our goalposts, right? It's centered around the null statement. And the question is, where are the goalposts? So how far do you want the goalpost away from the null? And then the next part is, well, where did the sample come in? Was it within the goalpost or outside of the goalpost? Now, since the null, just erase this, since the null is expressed as an equality, the goalpost must be set equidistant on either side of the null, resulting in a two-tailed test. And we've seen this from previous modules for hypothesis tests. The way the test is set up is based on how the null is presented. So if you have an equality in the null, that means you're willing to accept values equidistant on either side. So I'm willing to accept values on this side and that side, and these would be equidistant. So that gives us two tails. That's the first thing. So now to get the critical value, what we need to express, or what we need to define, is the degrees of freedom. And when you're doing tests for correlation, the degree of freedom is n-2 rather than n-1. So we just have to remember that. And then the other thing we have to specify is the single tail area. So first, degrees of freedom, we had 40 observations minus 2, that's 38 degrees of freedom. And the single tail area, so if you're sort of putting that 95% margin of error in the middle, that results in 2.5% on either tail. And again, what critical value is, it's going to tell us, well, how many standard deviations do we need to go, or do the goalposts need to be on either side? So ladies and gentlemen, let me tidy this up so we can focus on what counts. We have a degrees of freedom of 38 and a single tail area of 0.025. Now I'm going to take you to the t-table and show you where we got this number. And here we are. This is your t-distribution, and notice how we're required to specify the area of one of the tails. So there it is. The area of the tail is 0.025, and the degree of freedom that is relevant in our case is 38. So when we triangulate degrees of freedom with the tail area, we get a critical value of 2.024, which is right there. So what that tells us is that the goalpost needs to be 2.204 on either side of the null statement. So one of them would be plus 2.024 and the other one would be minus 2.024 standard deviations. So the goalposts are set up. Now the only question is, did the sample fall within this or outside of this range? And here it is. So for the sample statistic, it's the deviation of the sample correlation from the hypothesized population correlation. And here's how we find the sample statistic for correlation. Now, ladies and gentlemen, there aren't too many frameworks that I ask candidates to memorize. In fact, throughout the whole curriculum, there's probably no more than 10 frameworks or formulas. I hate the word formula, but there it is. So there's probably 10 formulas I'll ask you to memorize throughout the whole curriculum. And this will be one of them, because it's a lot easier to just commit this to memory than to build it from the ground up. So this is how we find the sample statistic for the correlation. And so we just plug in the sample correlation. So there it is. It's 0.06 multiplied by the square root of n-2. There it is. And then we divide it by 1 minus, again, the sample correlation squared. And then I show you what the numerator works out to and the denominator works out to. So we get a sample statistic of 4.62. So let's go back to our framework here. Again, remember, everything starts from the null. So whether you're looking at the critical values or whether you're looking at the sample statistic, it all starts from the null. So the sample is positive 4.62 standard deviations away from the null. So that would be right there. So do you see how I measure the sample's distance starting from the null? So our sample lies there. And then when you look up, you say, oh, that is alternative territory. So therefore, we are going to reject the null. And that's how you play the game. So the decision rule is as follows. Since the sample fell outside the null range, we would reject the null and therefore accept the alternative. But when you say accept the alternative, what does that mean in plain language? Well, why don't you go see what you wrote for the alternative? And this is why, ladies and gentlemen, a structured approach is really important, because it's right there. You don't have to make anything up. So you're accepting this. What does that say? It says that the population correlation is not equal to 0, meaning that it is significant. And there it is. So the population is not correlation is not equal to 0. It's significant. Now, the other thing you have to remember is the following. Because your whole test or your whole conclusion was based on a sample, it means that you're not 100% sure, because we don't know what the true population correlation is. So if you want to really answer this fully, you have to indicate how confident you are in your conclusion. And since we gave the null a 95% margin of error, and we still rejected it, so we can say we are 95% confident in our decision, or alternatively, we could say we are confident in our test at the 5% level of significance. So these two mean the same thing, but usually it's expressed in terms of level of significance. So when we say this is our conclusion at the 5% level of significance, what we're really saying is we are 95% confident in our conclusion.